Hello everyone, my name is Ratuddin and welcome back to another video about artificial intelligence and deep learning. This video will be based on 3 Blue 1 Brown's series on deep learning, specifically DL6 and DL7, so make sure to check those videos out because a lot of my information is based on that, and a lot of the diagrams I also use are from his videos straight up. I'll link them down in the description as usual. Check them out. I highly recommend it. He explains these topics way better than me. But let's get started. Today we're talking about large language models, specifically attention transformers, and how might large language models store facts. So, artificial intelligence has made incredible strides in recent years, particularly with large language models, or LLMs. These models can generate human like text, complete sentences, and even answer complex questions. But have you ever wondered how they actually store knowledge? How does an AI know that, for example, Michael Jordan plays basketball and not say soccer? So today we're diving deep into how AI stores facts, why researchers believe certain components of neural networks hold this knowledge, and how they can even be edited or altered. To understand how an AI like GPT-4, for example, knows things, let's start with how it predicts words. When you type Michael Jordan plays, the model calculates probabilities for different words based on patterns in the data it has seen. So in this case, basketball is the most likely prediction because how often Michael Jordan appears in text about the sport. So as we can see in the probability chart, it is an 80% chance that Michael Jordan is linked to basketball when we put in this phrase, Michael Jordan plays a sport of blank. So um, this raises a big question though. Where does this knowledge come from? It turns out that AI isn't just retrieving facts like a search engine. Instead, it encodes them within its neural network parameters. And that's where things get really interesting. Researchers at Google DeepMind investigated how large language models store facts, and their findings were fascinating to say the least. They discovered that certain parts of the model, specifically the multi-layer perceptrons, or MLPs as we call them, play a key role in storing factual knowledge. So here's how it works. When a word like Michael passes through the network, different layers modify its representation step by step. By the time it reaches the output, the MLP layers have associated Michael Jordan with basketball through millions of tiny adjustments in weight values. So think of it like this. If AI knowledge was stored in a giant warehouse, MLP layers would be like shelves organizing and categorizing everything so that when you ask a question, it knows where to look. Now, if you love math, this next part is for you, but I won't be going in depth like it like 3 Blue 1 Brown did. The way LLMs store facts boils down to matrix multiplications and activation functions. So each neuron in an MLP applies a transformation to the input, reinforcing certain patterns while filtering out irrelevant details. So one way to think of this is like an AND gate in logic. So if two inputs strongly match an existing fact, say Michael Jordan and basketball in our case, the neuron activates and strengthens that connection. So over time, this creates a highly reliable internal map of knowledge. So once again, I'm not going to go too in depth about it, but if you guys want to know more about this, check out 3 Blue Ones Brown's videos for sure. He covers this topic way better than I am. So the network diagram here shows connections getting stronger with each layer. So from one layer to the next, we can see that the values are getting stronger. But before we continue to talk about this and we move on, let's take a quick detour to talk about the softmax function. It's one of the key mathematical tools that helps AI determine probabilities. The softmax takes a list of numbers and converts them into probabilities that sum to 1. So let me just bring up VS Code to explain this easier. So, just, oops. So the reason that this works is simple. Softmax exponentiates each input value, making larger numbers grow exponentially compared to smaller ones. Then it normalizes the values by dividing each by the sum of all exponentials. This keeps the relative order of the numbers the same, but it stretches the differences, making the highest probability values significantly larger. So we can see that if I were to run this code right here, this is the softmax function using exponentiation, we can see that these values in the array start becoming bigger exponentially. So what if instead of an exponential curve, this function produces a more linear spread of probabilities? So instead of exponentiation, we just replace it with something like squaring each number instead. So let's modify the function to see how that changes things. So here I have a version with using squaring the elements instead of exponentiation, and let's run the code for this as well. So we can see that while the values are growing bigger, they're not growing as big as the ones from the exponentiation function. So basically what this shows us is how important, how crucial exponentiation is to softmax. It ensures that dominant probabilities stand out more sharply. Without it, the decision would be much less confident, because as we can see, uh, if we were to square it, there's not that big of a difference between each value. But then if we exponentiate, there's a very sharp increase from something like 0.23 to 0.63 in compared to the rest of the values. With that talked about, let's back over to our presentation over here. So what happens when we scale this up to a model like GPT-3 with hundreds of billions of parameters? The same principles apply, but at an enormous scale. Each layer refines the information, fine-tuning the probabilities of different word associations. The takeaway, AI doesn't store facts in just a simple list, it embeds them as weighted connections spread across millions of neurons. And this is what makes the model so powerful, yet so difficult to precisely control. So, this brings us to an exciting question. Can we edit these facts? What if an AI gets something wrong or needs an update? Researchers have found ways to fine-tune models on new data or even directly modify certain weights to correctly specify to correct specific facts without retraining the entire model. So, while this technology is still developing, it has big implications. Imagine an AI assistant that can learn and update its knowledge in real time without needing an entire dataset overhaul. So that's more or less for me. I hope this gave you a deeper understanding of how AI remembers things. Well, obviously quotes around remembers. If you found this interesting, don't forget to go check out Three Blue Ones Browns videos regarding the topic. I think they're highly informative, and they helped me learn a lot as well.